All right, so we're talking about symmetry of functions. So how if we're looking at the graph or we're looking at an equation, are they symmetric? And if so, how? So we have different options. We can have line symmetry, where if I draw a line straight down the middle of the graph, I can see either side is the same. Or we can have point symmetry, which is just going to be reflecting it over one specific point. So we have two types of line symmetry. We have y-axis and x-axis symmetry. And then we have one type of point symmetry, which is over the origin. And remember, the origin is that point 0, 0. All right, so I think the y-axis symmetry is the most obvious kind of. It's the one that we think of the most when we think about symmetry. That's any time that the y-axis is taking our graph and splitting it in half. So if I'm looking at this parabola, I can see that the y-axis right down the middle splits my graph in half. It's the same on both sides of the y-axis. The most important thing about y-axis symmetry is for any point x, y, I also have the same point, but my x is going to be negative. So if I have the point 1, 2, I also have to have negative 1, 2. So, for example, if so my y values are staying the same, but for every x value I have, I also have to have a negative x value. So if I'm looking at the graph, it's easy because I'm just looking to see if the y-axis splits it right in half. If I'm looking at an actual equation, I have to check to make sure that every time I have a point xy, I also have negative xy. And I'm going to show you how to do that after we look at the different shapes of graphs. If I have x-axis symmetry, that means I'm just taking my graph and my x-axis is cutting my graph in half. So if this is my parabola, this time my x-axis cuts it in half. Is something like this going to be a function? No, right? It's never going to be a function if I have the same thing on both sides of the x-axis. So anytime I'm talking about actual functions, they shouldn't have x-axis symmetry because they can't be a function and have x-axis symmetry. in this situation, anytime I have xy, now I have my same x value, but a negative y value. So for each point, x, comma, y, I also have x, comma, negative y. And I can see that right here. They're saying, okay, if I have this point xy, I also have the same point where I went over the same amount of x values, but now instead of going up, I went down those y values. So I think these two are the easiest for us to see because they're the types of lines of symmetry that we're used to drawing in art class, that we're used to seeing back in elementary school, where they would give us half of the picture and ask us to make the other half, or they would ask us just to draw the line that split the shape right in half, are points of symmetry. So when we look at the origin as symmetry is a little bit trickier because it's taking all of our points and reflecting them across the origin. So anything that I have in quadrant 1, I have to also have in quadrant 3. And quadrant 2 gets reflected to quadrant 4. So it's a little bit wackier in the sense that it's not our simple line of symmetry that we're used to drawing, because we're actually physically reflecting it over a point. So I take anything in quadrant 1 and flip it so that it also is in quadrant 3, and it flips over the origin. And then anything in quadrant 2 reflects over the origin into quadrant 4. Or basically, whatever point I have, so if I have xy, I also have to have negative x, negative y. So I'm changing the signs of both points this time. So I'm changing the value or the sign of my x value and my y value this time. So when I have, for example, if I have 2, 3, then I also have negative 2, negative 3. So the easiest way for you to check is to kind of pick out a point on the graph. So if I went over to the graph and I said, okay, let's see. I'm going to pick out the prettiest point I can find, which this looks like it's almost 2, 1. And then that means, or 3, 1. That means I also have to have the point negative 3, negative 1. So then I want to go back to negative 3, down to 1, and make sure that I also have the point negative 3, negative 1. And I would do that for a couple points and just check to make sure that I have the opposites. So if I asked you to look at the graphs below and determine the types of symmetry they have. So these are the types of questions you're going to see today. Look at the graph and decide, does it have x-axis symmetry? Does it have y-axis symmetry? Is it reflected over the origin? Or it could be completely different. It might not have symmetry at all. That is possible. So we will have an option of like no symmetry when we're looking at the classwork. So if I look at that first one, A looks like a big old W. So right off the bat, I look at it and I say, okay, well, it's symmetric, definitely. Is it symmetric over the y-axis, the x-axis, or the origin? The y-axis, right? Because if I look at my y-axis, splits it right down the middle. So this is symmetric over the y-axis. What about B? It's over the origin, right? It's kind of, it looks kind of the same, but it's like reverse of each other over the origin. What about C? X-axis, right? What if I took this circle and I moved it so it was centered at the origin? Origin. What else? X-axis and y-axis, right? So it could be multiple. It could have a couple. That is possible. So in this situation, now I have the x-axis. I also have the y-axis and the origin if I kept it in the middle, because all of these ways it's symmetric over all of those. So you could have more than one. Most of the time, though, if we're talking about your actual functions, you're only going to have one type of symmetry. A circle, isn't a function, right? It fails the vertical line test. So it's those things that aren't functions that can get a little wacky and have kind of lots of different answers for them. What about D? Origin. Yeah. Does D look like a graph you know? Ooh, it looks like the sine function, right? It is the sine function. Oop, origin. You want to try it. The sine function is symmetric over the origin. So looking at the graphs should be the easy peasy part. It's when I give you an equation that gets a little bit trickier and I ask you to prove if the equation is symmetric or not. So if I just gave you an equation and asked you to tell me if it had symmetry, and you were trying to be the most time-efficient mathematician you could possibly be, I would pull out Desmos, type in the equation, right, and look at the graph, because looking at the graph is going to be the easiest way. Or even if you want to check yourself when you're proving to make sure you're proving the correct thing, you use Desmos to get a picture of the graph. But some of your classwork is going to actually ask you to prove if an equation has x or y-axis symmetry or origin symmetry. So in order to do that, so if I gave you determine if x squared minus 2y equals 3 is symmetric over the y-axis, the first thing you're going to need to know is if you have any point xy and you're symmetric over the y-axis, you need to know what happens to those points when you're symmetric over the y-axis. So those little tips that we wrote down in the beginning. Now, instead of memorizing those, I just kind of like to think about it. And I say to myself, okay, if I'm talking about a graph that's symmetric over the y-axis, that means it's like my parabola, right? And if I have a point on my parabola in the first quadrant, it's going to be x comma y. I also have to have a point in my second quadrant. So my second quadrant, I have negative x values and positive y values when I graph those. So you are more than free to just memorize that when it's y-axis symmetry, you have the point xy and negative xy, or you can just kind of draw yourself a picture and think about it to see which ones you have. I like to just think about it because sometimes it's a little tricky and over time you may forget. So this way, at least, if you do forget what it is, you can always check yourself. So because I know that my equation has to have this negative x, negative y, what I'm going to do is I'm going to take the equation they gave me, my x squared minus 2y equals 3. And I'm going to substitute in a negative x and a y where I have my positive x and my positive y. So where I had x and y, I want to replace it with the point I know I have to have. So instead of having an x, I'm going to replace it with negative x. I'm going to keep everything else the same. Where I had a y, I'm still going to have a positive y because when I look at my point over here, this y is still positive. I'm just plugging in my x and my y here. Equals still 3. And then what I want to do is I want to see if I can mathematically manipulate the equation to get back to where I started. If I can get back to that original x squared minus 2y equals 3, if I can make it the same as my original, that means it's symmetric. If I can't get rid of that negative sign, or if it ends up looking different, that means it's not symmetric. So I want it to be the same. Now I know all about the importance of protection. So I know when negative x is squared like that, what is that the same as? What happens when you square a negative? It becomes positive, right? So this entire thing is really the same exact thing as saying x squared minus, even though I have parentheses around my y, 2 times the quantity of y is just 2y equals 3. So even though I plugged in a negative x into my equation, it didn't change anything because when I square a negative number, I'm still going to get out the same number. Does that make sense? Yeah. So because I didn't change anything, because I was able to get my equation to look exactly the same, this is going to have y-axis symmetry. You could also, if you don't love using x and y, you could pick a point like 1, 2, plug it in, see what you get, and then plug in negative 1, 2, and see if you get the same thing. If I gave you a different equation and asked you to decide, so if I give you x plus 3y squared plus 4 equals 0, and asked you to determine if it was symmetric over the x-axis, we're going to take the same steps, but we have to plug in the point combo that works for our x-axis. So when I'm looking at x-axis, I know that's like my sideways parabolas, right? So my original equation has x and y in it. If it was symmetric, it should also be the same if it has positive x and negative y in it. So I need to plug in a positive x and a negative y and see if I can manipulate it to be exactly the same. So I'm going to take my x plus 3y squared plus 4 equals 0. And where I had an x, I'm replacing it with an x, so nothing's going to change. Where I have a y, I'm replacing it with a negative y. And then I just want to go through and make sure that it still comes out to be x plus 3y squared plus 4. I didn't change my x, I just changed its color. Still an x. And I know from the last problem that when I square a negative, it's the same thing, it makes it positive, right? So I really still have 3y squared here plus 4 equals 0. So even though I plugged in a negative y, it didn't change my equation at all, so this is symmetric over the x-axis. What could I change to make it not symmetric over the x-axis? If I remove the squared, right, if the squared wasn't there, the negative would stay. Or if it was to an odd power, right, if it was a 3 or a 5, any odd power is going to keep the negative because I'll have pairs of negatives with one left over when I have odd powers. So if that negative doesn't go away when I raise it to the exponent, that's when it wouldn't have symmetry. So this is symmetric to the x-axis. All right, this last example wants to know if x minus 2y squared equals 5 is symmetric to the origin. So I know when I'm looking at origin, if I didn't remember, it was things that looked like this. And for any time I was plugging in x and y, I also have to have negative x and negative y. So I need to take my equation and I need to replace my x and my y with a negative x and a negative y and see if it comes out to be the same. So I've got x minus 2y squared equals 5. I'm going to take this negative x and plug it in for my x. Bring down my minus 2. Now I'm going to change my y to be a negative y. And then I want to look and see if I can get it to be the same. Is there anything I can do to that negative x that's going to make it positive? No, right? There's nothing else happening to that negative x. It just has become negative. So because there is nothing I can do here, this is never going to become positive. It's never going to get back to matching my original equation. This is not symmetric over the origin. So that's what I was talking about with saying you have to see if it matches. If you can get it to match, it's symmetric. If it doesn't match, if it's not exactly the same, then it's not symmetric. So not It's not symmetric because the x became negative and there's nothing I can do there in order to fix that. That was symmetric?
Yeah.
So if it would have to probably, they would both have to be squared, right? Or they would both have to, they'd have to stay the same. Because the y is going to go back, right? The 2y squared will end up being 2y squared because we're squaring it again. So if it was x squared and y squared, they would both go back to being positive. Any even power will keep it positive.